Okay, we're actually going to start out by just reading the problem, then we're going to draw a picture, then we're going to figure out how to analyze the problem. Your shot. Please read the problem 3.
You're wearing your rocket pack that accelerates you upward in a constant 10.5 meters per second squared. While preparing to take pictures of a beautiful view, you drop your camera 5.0 seconds after liftoff. Hey, what is the camera's velocity after an additional 5.0 seconds?
We're going to do part B as well.
Okay. How far are you from the camera at this time?
So, you are wearing your rocket pack. In the event that you are wearing your rocket pack, you should also be wearing a helmet with a face guard and probably a... This is your camera. We're going to launch the rocket. You go up. 5 seconds after liftoff, you drop the camera. You continue to move upward. The camera is originally going to go upward with you and eventually will fall back down. So this is the camera. This is you after the other 5 seconds. So we have part 1. Notice for part 1, both you and the camera are together. Then we have part 2. Part 2, you and the camera are separate. So notice that you have to identify 2 different parts for part 2. So we have part 1, where both of you are together. Then we have part 2, where we can talk about just you, and then we have part 2 for just the camera. We've read the problem. There are a bunch of different pieces of information. Let's start listing them and putting them in the right spots. Austin, give me some. A known variable and where it needs to go.
The acceleration is 10.5 meters per second squared.
The acceleration for what? For which part?
Part 1 and you and the camera.
So for both of you, the acceleration for part 1, bless you, is 10.5 meters per second squared. Agreed. What else? Frederick.
The time for part 1 is 5 seconds.
The delta t, the change in time for part 1, is 5.0 seconds. Agreed. More stuff. Mike. More stuff.
Total mass is 75 kilograms.
The total mass is 75 kilograms. Arjun, why does it say the total mass is 75 kilograms on this problem? Why would I put this on the problem? I would never put something on there to throw you off. That would be me. Why would I put it on there, Susan? Why?
To show that mass doesn't matter.
To remind you that mass is irrelevant. To throw you off, aren't you? You should look at it and go, oh, I know mass is irrelevant. That seems silly. Why would he give that to us? That must be to remind us that mass is irrelevant. More stuff. What else do we know? Spencer?
Initial velocity is 0.
Part 1, part 2? For part 1. Part 1. So velocity for part 1 initial is equal to 0. I'm going to stop for a moment. What have we identified now about part 1? Claire?
That
We listed everything we know so far. Everything we listed we know so far about part 1. So what do we know more generally about part 1?
started on the ground.
Yeah, that's not quite what I'm looking for. That's okay. Frank? We see the acceleration equals a number, so we can use the uniformly accelerated motion equations. What else, James? Not only that. Time is constant. That's an interesting statement. The time is 5 seconds. I'm not sure if we can call that constant. How many UAM variables do we know for part 1 class?
3.
This is enough, right?
Yeah.
So we know right now we could start with part 1. We could solve for the other 2 for part 1. Let's list what else we know for parts 2 for you and part 2 for the camera. Zach, give me something else.
For part 2 of the camera, the acceleration is negative 9.8 meters per second squared.
The acceleration for part 2 for the camera is equal to negative 9.8 meters per second squared. You know this because?
That is the acceleration of gravity.
The acceleration due to gravity, yes, but how do we know that the camera has this, Spencer?
It's in free fall.
Because this object is now an object in free fall. Once you drop it, it becomes an object flying through the vacuum that you can breathe. It's not touching anything else. Therefore, it's in free fall. Great. What else? Christine?
You drop it after 5 seconds, so.
That's change time for part 1. That was 5 seconds.
So for camera, we can also do, time is 5 seconds.
The change in time for the second part is 5.0 seconds, and that's independent of the object. So I would put that down for both of them and just label it change in time for part 2 is 5.0 seconds. Your shot.
Well, I mean, if you solve part 1, then you can find velocity initial for the camera.
So if we solve what for part 1
You find velocity 1 final
is equal to,
is equal to is equal to velocity 1 initial plus.
oh, I'm sorry, you're trying to solve the problem. I thought you were trying to give me a relationship.
Oh, I mean.
Go ahead.
All right. Velocity 1 initial plus acceleration 1 times delta t1.
Change in
Delta
time for
time
part
change
1.
times.
Great. There's one more variable. Before we do that, that's definitely what we're going to do next. But before we do that, Frank,
Velocity final part 1 equals velocity initial part 2.
more specifically,
Velocity.
that's not quite enough. Spencer,
5,700. Velocity.
for which object?
For the camera.
But it's also true for you, right? This is the velocity at that specific moment. It is both the final velocity for part 1, but it is also the initial velocity for part 2 for you and for part 2 for the camera. Keeper?
You wrote it velocity 1 initial, shouldn't it be velocity final?
Fine. Yeah.
Thank you.
Initial?
Velocity 1 final. Thank you much. Thanks.
Don't we still need velocity 1 initial equals 0?
Ah, yes, that would be why. That's where I ran into the issue. Okay, thank you. I was wondering what happened there. Got it. Thank you. Spencer,
The acceleration for part 2 is still 10.5.
for you, right?
Yes.
Because you are still wearing the rocket. Great. All right. So we now have all the information we need. Velocity for part 1 initial was 0, plus the acceleration for part 1, 10.5, times the change time for part 1, which is 5. Therefore, velocity 1 final is 52.5 meters per second, which is the same as the velocity initial for part 2 for you, and the velocity for part 2 initial for the camera. So I can now write those down here. 2 initial of you, the initial velocity is 52.5 meters per second, and the velocity for part 2 initial for the camera is 52.5 meters per second. And you can now see for both of our parts 2, we know 3 of our UAM variables we can solve for the other 2. Karen, what now? True. There are so many. So we're talking part 2 for the camera. Go ahead. Hold up, you're missing a subscript. Notice, we need all 3 of these subscripts, right? This is the velocity for part 2, the final velocity for the camera. 3 different subscripts, but we need them all. Keep going. A lot of subscripts, but they're all very useful. This is the velocity for part 2 initial for the camera. This is the acceleration for part 2 for the camera, and the change in time for part 2. So the velocity initial for part 2 for the camera was the 52.5. The acceleration for part 2 for the camera was a negative 9.8. And the change in time for part 2 was 5 seconds. The velocity for part 2 final for the camera is equal to, please. 3.5 meters per second. And it was at this point that we got our answer, and many of you looked at this answer and you were unhappy. This made you feel uncomfortable inside. What is it about this answer that you did not like? Mike? It's positive, which means what about the camera, Ezra? It's still moving up. I had several people who just decided to put a negative on here because they said, well, we know the camera's moving down. Do we know the camera's moving down? No, in fact, we know the camera's still moving up because we got a positive answer. That means that we drew our picture wrong. We need to come back and redraw our picture. It turns out that the camera has not reached the top of its arc yet. The camera is right here. It's very close to the top of its arc, because this velocity is close to 0. Very soon it will reach 0 and then it will go negative. But at the moment it is still happens to be moving up. Good, we figured out the velocity for part 2, final for the camera. Rishad, what now? Where did we lose you? Well, we've solved part A, so sure, part B. Part B, to remind you, is the distance between you and the camera, which is this, right there, visually. Rishad. What do we need to find in order to find this? Rishad, tell me what we're trying to find. How far you are away from the camera. What are the dimensions on that? That's not a dimension. Class, dimensions are your friends. What are the dimensions on the distance between you and the camera, class? What is the only one of the UAM variables that has this dimension?
That's the one.
The displacement, right? So we need to find the displacements for both you and the camera. Eric.
We could use the equation
Where am I putting it?
for part 2 for you. We could use delta y equals u. Equals the velocity initial for part 2 for you, times the change in time for part 2, plus 1/2 times the acceleration part 2 for you, times the change in time for part 2 squared.
Good, we have all these variables. The initial was 52.5, change in time is 5, plus 1/2 times the acceleration, 10.5 times the change in time, which we're going to square. The change in y for part 2 for you is? 300?
200 feet.
Sorry. 393.75 meters. We have figured out the displacement in the y direction of you from the moment you dropped the camera. Trevor, what now?
Now you can figure out the displacement for the part 2 camera.
Okay, so I'm going to continue with part 2 for the camera.
Delta y c2 equals velocity initial c2
Okay, let's stop using C and 2. Velocity initial
camera 2 or part 2
for
camera
part 2 for the camera. Good.
times delta time part 2
The change in time for part 2.
plus 1/2 acceleration to camera part 2 times delta t part 2 squared.
So 52.5 times 5 plus 1/2 times negative 9.8 times 5 squared. The displacement in the y direction for part 2 for the camera equals 140 meters. So the distance between you and the camera, we have figured out the displacement in the y direction for part 2 for the camera, visually on the board right there. Lindsay, the distance between you and the camera then is going to be equal to?
It would be equal to the distance, okay, changing y to u.
Okay, hold up. You did a very good job of telling me what the letters are.
Okay.
This is, delta y is called
Changing.
the displacement or the change of position
Yeah. The second part
for you.
for you, minus the displacement for the second part of the camera.
You can see visually that in order to figure out this distance b, we need to take the displacement for part 2 for the camera and subtract it for the displacement for part 2 for you. So it's going to be equal to 393.75 minus 140, or 253.75 with safe face, 250 meters. Taking a few moments to reflect on what we just did, which we're going to do after we answer the question from Eric.
Do we have to write like the magnitude lines? On
In this particular case, was it the magnitude?
I guess not.
No. If we had to, then yes.
Okay.
Tish.
Can change in time ever be negative?
Can change in time ever be negative? That is an interesting question. The answer is, of course, yes. In this class, I'm going to say I can't think of a time that we'll ever have a negative time in this class. In life, yes. In AP, certainly.
Okay.
Okay. So just to take a moment to reflect on what we did. Did you guys have a question? Karen? Yes. I did the displacement for part 2 for you, and I subtracted the displacement for part 2 from the camera from. Okay. I just started with a picture. This problem was complicated enough that starting with a picture was actually a really good place to start. Therefore, we were able to identify we had part 1, part 2 for you, and part 2 for the camera. Then we listed everything that we knew, and then from there, it was just basically using the UIM equations and using liberal subscripts to keep track of everything, because there were a lot of different velocities and accelerations. True? Please identify that that's a useful way to do stuff.